In this final section, we're just going to go through some examples and pull a lot of information out of different structures so we can see how you might match a structure to a spectrum, and some examples where IR could be pretty useful in distinguishing different compounds. One of the things that students often mistake is thinking that they should be able to deduce a complete structure from an IR spectrum. And for most students, that is just pretty much impossible to do. Really, you just want to get a lot of information about the functional groups out of it, just so that you can have some clues as to what the structure is. So let's look at some examples, and we'll go through and figure out some distinguishing features. So the first one that we're going to look at is just this alkene compound. First, we're going to look up here in the 3000 region, and we have a signal just above 3000 wave numbers. Remember, that is CsP2 hydrogen stretches. So that's going to correspond to these CHs on the alkene. But then just below 3000, this is the CsP3 hydrogen stretches. So that's all of these CsP3 carbons with hydrogens on them. So that's where their stretches are showing up. Next, as we move down the spectrum, we have a pretty distinct signal right around 1650 wave numbers. And that is the carbon-carbon double bond stretch. So that's what corresponds to this carbon-carbon double bond. A couple other small things that we can pull out of this have to do with some of the bending motions. Here's 1400 wave numbers, and just above 1400 we have a pretty distinct signal, and that is likely all of these CH2 bending frequencies. And then just below 1400 wave numbers, this is from the methyl groups bending. So we have two methyl groups. So all of these things we can sort of put together and come up with some of the features of this molecule. Next, we can look at this alcohol that has both an alcohol functional group and an alkyne in it. And we can pull some things out of this spectrum. First, the most distinguishing thing in the spectrum is the OH stretch. And that is sort of this broad peak here. That's the OH stretch, right around 3400. Now, because we have a terminal alkyne, we should also see this alkyne carbon-hydrogen stretch here at about 3300. Now, it's sort of buried within this alcohol, but we can see this extra sharp peak coming out of the alcohol peak, and that is that alkyne CH. Now, right below 3000, we have a couple of signals. And remember, just below 3000 is a CsP3 carbon-hydrogen stretches. So that likely corresponds to these CH stretches there. Another distinguishing signal is this peak right at about 2100 wave numbers. And that distinguishes this carbon-carbon triple bond stretch. One last signal to point out here that is really well defined is the signal at 1050. And that corresponds to the carbon-oxygen stretch. So that is an sp3 carbon oxygen single bond stretch. So these are some of the features we can pull out of this molecule and identify within the spectrum. Next we have this amide, and the first thing we see is some sharp peaks right here between 31 and 3400 wave numbers. Now these peaks correspond to the NH2. Remember, if we have two hydrogens on nitrogen, we should see two peaks. And that's what we see right here. We see one that looks to be at about 3150, and one that looks to be at about 3350. Now these are at a slightly lower stretching frequency than what you would see with amines, and that's to be expected with amides. So amide nitrogens, those NH stretches, are at a lower stretching frequency than amines. So that's just something to look out for. Now we should also expect to see sp2 carbon hydrogen stretches. Remember, those show up just above 3000, and they're actually pretty hard to see in this spectrum because they're sort of buried under the NH stretches, but we can see possibly a couple of those peeking through in this spectrum. Another thing that we can identify, which is very diagnostic, is the C double bond O carbonyl stretch of the amide. And that is right here at about 1680 wave numbers. Because it's in conjugation, it's slightly lower than you might expect, but in general, amides are the low end anyways. Another thing that we can point out in the spectrum is the carbon-carbon double bond stretch right around 1600 wave numbers. And that is lower than expected, again because of conjugation. This double bond has some single bond character, lowering its stretching frequency. Next we're going to look at the IR of ethyl benzyl ketone. And there's a number of things we can pull out of this spectrum. First, we'll kind of do our basic cutoff here at 3000 wave numbers. To the left of 3000 wave numbers, these signals are our carbon sp2 hydrogen bonds, and although they're part of a benzene ring, they're still responsible for those stretches. To the right of 3000 wave numbers, this stuff over here, that is the carbon sp3 hydrogen bonds, and of course we have a number of those. The next thing we can look at is this signal right around 1710 wave numbers, and that is our carbonyl stretch, our C double bond O. Because we have this benzene ring, we should have some very specific stretches in this spectrum that represent that. The first is this stretch right around 1600. Then we have one right at 1500 and one just less than 1500 wave numbers. These three signals are representative of an aromatic ring. One other thing we can pull out of here pretty easily is this signal just less than 1400, and that is representative of a methyl group. and that's this methyl group right here. So these are a few of the things that we can pull out of this spectrum. One of the things that IR is often used for is to determine between some similar isomers. Because all of these compounds have the same molecular formula, C4H8O2, but they have different functional groups, so we can use IR to distinguish them. So just a few things before we look at spectra that we should be able to say here. So all have a carbonyl. So in all the spectra, we're going to see a carbonyl stretch, and that's going to be somewhere between 17 and 1750 wave numbers. The next thing we can say is this ester here, we're not going to see an OH stretch. But in both of these two compounds, we're going to see an OH. But the first one is just a regular primary alcohol, and we would expect to see that around 32 to 3600. However, the carboxylic acid OH, we would expect to see that around 3000 wave numbers. Additionally, with this compound, we should see a CsP3 oxygen stretch. With the carboxylic acid, we won't see any CsP3 carbon oxygen stretch, but we'll see a CsP2 carbon oxygen stretch, and then in the ester we'll see both. So we should be able to differentiate the spectra between these three. In this first one, the first thing you should see, well, there's no OH stretch. So most likely this is going to correspond to the ethyl acetate. Because this compound you wouldn't have an OH stretch. But what we do see, we see the carbonyl, we see some CsP3H stretches. We also see right here at about 1250 the carbon sp2 oxygen stretch, and right here at 1050 the carbon sp3 oxygen stretch. This one corresponds to this bond, and this one corresponds to that bond. The next one we have here, right here around 3400 wave numbers, is our OH. Right here just less than 3000, CsP3H stretches, which we have in this molecule. Right here just above 1700, that's our carbonyl. And then here at about 1050, that is our carbon sp3 oxygen stretch. So those are the main things you can pull out of this one. Our third spectrum must be the carboxylic acid, which we can see here. Now we still have this broad OH stretch, but now it's moved down to about 3000 wave numbers. So we can kind of see it here. And that is diagnostic of a carboxylic acid OH. We also have the carbonyl, which is just above 1700. And then kind of buried in here with the OH stretch here below 3000, again our CsP3 hydrogens. And then you can see here just above 1200, that is our CsP2 oxygen stretch. And that corresponds to our carboxylic acid.